Hello, we're going to work a typical type of AP Physics C problem that I like to call linearization of data. And I'm going to try to convince you that it's a commonly occurring type of problem on the AP exam and show you how to recognize it and show you how to do any type of problem that's like this. They all kind of work the same and show you the pattern, how it kind of works out. We're going to work this 2005 example. What you'll recognize is they'll give you a data table with some empty columns or rows, and you'll have a couple columns given, and you got to transform these in a way so that the newly calculated columns on there become basically the vertical and horizontal axes for a graph you're going to make, where it's going to linearize the data. It should be in like a straight line, and you can plot a best fit line, and the slope is going to be the constant that you're looking for. So like the spring constant for a spring, or the mass of a planet, or the universal gravitational constant, or whatever, any constant you can do an experiment kind of like this to figure out what's the constant that relates two separate groups of data together. So let's go through and check this out a little bit more. So I'm gonna go here and just look. I bet I can go 3 for 3 here. I bet I can go 2018, 17, 16 and show you that it shows up on each test. So here we go. Okay, and once again, we're looking for that data table that needs finished and a big graph looking thing. Oh, right there, and sure enough, right there. Okay. So you use the straight line and calculate the experimental value for gravity. Okay, let's go to another one. Let's go down to the very next year. Very common type of question. Okay, oh, I can see it right there. There's the data table that needs filled in, and there's the graph. Use your straight line to determine the experimental value for G, and G is one that comes up quite a bit on these. Okay, and let's go down to 2016. Bet we can find one there. They're pretty easy to spot, and when you see them, they take a little bit of labor to do, but boy, if you know how to do one of these, they all kind of behave very similarly, and they can be easy points for you on the exam. Oh, so I see a data table right there, and here's that. Use the straight line from the graph to calculate the mass of the cart. So, yeah. Anyways, really good to know how to do one of these, and it's really interesting to understand how they did find all these constants that they throw out at you in a physics class. This is kind of how they do it. All right, so we're going to tackle 2005 mechanics question number 2 here, and so here we go. A student is given a set of orbital data for some of the moons of Saturn, as shown below, and is asked to use the data to determine the mass of Saturn. Assume the orbits of these moons are circular. Okay, so we're given the orbital period, how long it takes to go around the planet for that moon. It's given in seconds. We have the orbital radius, r given in meters here, and so we're going to anticipate we need to kind of convert these over to transform this data somehow. And here's a nice picture. Maybe this is the right here. This is the mass of Saturn, and we have all these little moons going around them. And in our equation, like one of these moons would be like our lowercase m. Okay, so write an algebraic expression for the gravitational force between Saturn and one of its moons. Okay, so that's pretty straightforward. A lot of times they give us a leading question, and I don't think this one's super tough at all. So the force of gravity is, you should know this by heart if you're in the class, is big mass of Saturn and the little mass of one of the moons, and you divide it by the square of the distance from their centers of mass. And that's one of the questions. Okay, so we'll go to the next one. Use your expression from part A and the assumption of circular orbits to determine the equation for the orbital period t of a moon as a function of the orbital radius. So in these questions, you have to come up with some kind of algorithm or equation that describes a certain property of what this data came from. And so we're going to use centripetal force to help us with this one. I'm going to draw a diagram. Okay, so here's a little diagram of what we're talking about. One of these moons is, if it's orbiting around the planet of Saturn, is basically free falling around the planet in such a way it has a perfect balance between the force of gravity pulling it in and the momentum that wants it to go off tangentially. This balance makes it just curve perfectly and stay in this perfectly circular orbit around this planet, okay? And so the net force, the only force acting on it is the force of gravity, so that's the centripetal force and it's pointing directly in towards the planet. And so we have centripetal acceleration here and some tangential velocity. And so let's write a Newton's second law equation describing this centripetal action and this orbital speed that it's at. Okay, so we're going to apply Newton's second law, and we're going to sum the forces in the radial direction, and that's going to be a centripetal acceleration. So we know the equation for centripetal acceleration is v squared over r. And when we look at the speed this little moon would take to go around this planet in a circular orbit, it would do one circumference in one period of time. So a circumference is 2 pi r, and then we bring the 2 over here. So those are some things we're going to apply into this equation. Let me write out our Newton's second law equation now. Okay, so we've written out the force acting on the moon is the force of gravity, and that's going to make the mass accelerate centripetally. And we've shown where we substituted in v squared over r for the acceleration here. Next thing I need to do is sprinkle in the details of this force of gravity, which we already wrote out right here. Okay, so we've substituted in the force of gravity here. The next thing I'm going to do, I'm going to start sprinkling in this for our v here. But before I do that, I'm going to go ahead and send some of my stuff. I'm going to simplify this a little bit. I can get rid of some stuff here. By the way, I just want to emphasize, my system is the moon, okay? And so it's the mass that's being accelerated. It's this little m in this case, okay? The big M of Saturn is pulling on it. Now, I can see that I have an m on both sides. The mass of the moon is responsible for producing the force that accelerates it, but it's also responsible for resisting acceleration. So that effect cancels out in this situation. And similarly, R is gonna, we're gonna get rid of some R action here. Okay, and now I'm gonna put in this stuff. Okay, so once again for this speed of our moon around the planet, we're going to plug in what it means to do an orbit in a period. So we plug that into that spot. That whole thing is going to get squared, and we'll distribute the square through here now. Okay, so when we distribute that square, everything in here gets squared, and we end up with 2 squared, which is 4, pi squared, r cubed, because we had an r that we brought multiplied both sides to bring it onto the top on the right hand side of the equation. So that made us have this r squared plus this r, multiplied times this r on the other side, and t squared on the bottom. We end up with something like this. Next thing, I'm going to go ahead and solve for the orbital period t of the moon as a function of r. Okay, so when we get t by itself, we're going to go ahead and multiply on both sides by t squared. That will flip it over to the left-hand side and cancel it out over here. And then we're going to divide away, put this stuff on the bottom. And we could simplify just a little bit here by saying, bringing out this 4 and this pi squared out in front. We get something like this, and this would be a fine answer. Okay, let's move on to the next part here. So, by the way, once again, we're just understanding what it means to be in a free fall around a planet. That means you're orbiting around the planet, and basically you have centripetal acceleration. All right, let's go down here. Which quantities should be graphed to yield a straight line whose slope could be used to determine Saturn's mass? Okay, so we could make a graph that basically takes this piece right here and solves a way for mass of Saturn, gets it by itself. And when we have this graph, the top part could be our vertical axis, Or, in other words, this could be like, we could make this the rise of a linear graph. And the bottom part of this equation could be the run for our graph. Run. And when we do this, this should produce a linearized graph that we could do a best fit line, and we could just pick up any 2 points along this graph, and the slope of this line is going to be our mass of Saturn right here. Okay? And so which quantity should be graphed to yield this? So I would just go over here. I would actually just sketch this real quick and take this equation and show like where you got it from and identify rise and run. And then I just one more time just be perfectly crystal clear. I just write vertical axis. And I just clarify, I just be super clear here. And maybe I should put that in a different color, but anyways, vertical axis is going to be 4 pi squared r cubed, and horizontal axis is going to be gt squared. And there you go. That's essentially how every one of these problems is going to work out. This linearization problem is you're going to have some kind of relationship, whatever property the whole problem is about and what the data is collected for. And you're going to find that relationship, and then you're going to like isolate for the variable that you would like to solve for the not the variable, the constant you would like to solve for. And when you set up a graph like this, the slope of that straight line is going to be what that constant is. And so you take all this data, you adjust different variables, and it's going to produce a bunch of data points like this, and you can take the slope. Okay, complete the data table by calculating the 2 quantities to be graphed. Label the top of each column, including units. Okay, so we're going to go up to this table right here, and we're going to transform all this data basically into this and this for the columns. Okay, so basically for this orbital period stuff, I take that and I transform it according to this equation into this stuff over here, and I just take this and throw it in there, and I get this, and I just go ahead and transform all that data for the first column into this right-hand column. And then for the orbital radius, I basically take this information and plug it in to this equation right here to get this data right here. And as I went through, I noticed I was getting some different values. I made sure I had it all relative to e to the 26th, and if you're not familiar with that, e is just in your calculator just means times 10 to the whatever power. So this says 2.5 times 10 to the 26th power is what this means right here, okay? And so I made sure I put in my units right here. This one is pretty easy. This is the only thing in here that has units, so it's meters cubed. But over here, this constant has units, which if you look it up on your equation sheet for the test, is this. T is in seconds, as you can see right here. So I just kind of mushed all this together right here. You could simplify this, but this is a time test, and I don't care to do it. So I'm just going to like look it up and throw the stuff in there, and that's what they wanted, and I'm good to go. Okay, and so you basically just run this out in your calculator. So that's a little bit labor intensive, but once again, once you see a couple of these problems, it's basically autopilot for these, assuming you can get the relationship for the main idea they're using. Okay, and so basically we produce some data that we can graph according to what our vertical and horizontal axes are. And then from there, we've got our data table made. What's the next thing they say? Plot the graph on the axes below and label the axes with the variables and use appropriate numbers to indicate the scale. Okay, so you don't have to put a whole bunch of detail in here, just enough that they can get the idea. And please know this is a time test, so accuracy is not of the utmost importance. It's communicating that you know how, like, you know what you're doing to make this graph and pull the slope off of here. So don't be so worried about accuracy. You want to communicate, you know, like how to find it. Okay, so I'm going to go ahead and set that up. Okay, so I've labeled my axes here. And next thing that's important is we're going to try to figure out what's our scale we want to use. We want to try to use the bulk of the space. We don't want to fit it in a little postage stamp over here in the corner. So I'm going to just take a moment and try to be thoughtful about find a reasonable scale that uses a good amount of the space. So for the vertical axis, I'm seeing that maybe I could go from 0 all the way up to like, I don't know, 25. I got to go past this. So maybe I could go by 5s for that and have the scale be by times 10 to the 26th. So let's go do that. Okay, so please note I've put in the units here that this is times 10 to the 26th. That way I don't have to write it all over the place. I can save myself some time on this timed test. And I went just every one of these big like dark cross points on the scale. I put in a point. Please do not label every point on there. No one wants to read it and you don't want to write it. Okay, and let's go do the horizontal axis. So if we go up to that guy, the scale looks like maybe I can just go by 1s up to 5 maybe would be fine. And yeah, let's go ahead and crank that out. Oh, by the way, our equation has no, like our relationship we're doing here, has no y-intercept. It's going to be like going through the 0 point here. So just keep that in mind. I'm just mentioning that because I'm trying to figure out what my scale is going to be. I'm going to have it start from 0 because it should, my best fit line should cross right there. Okay, so I picked a scale where I was going by quarters basically, and I only labeled the whole numbers as I went up through here, and this should be enough. And so I'm going to use up a good amount of the space of the graph. And now I'm going to go and try to plot my data points. So my first data point here is going to be 2.5 and almost a half. So I'm going to go plot that. 2.5, 1, 2, 2.5, and almost a half, just a little bit shy of a half. So 0.25, 0.5 is right here. So I'm going to be like maybe around here somewhere. A nice big fat dot there. Remember, accuracy isn't the big deal here. In real life, you can put this in a computer and plot a best fit line, but we just want to make sure we're communicating the method of how to do this. I'm going to go ahead and plot the other ones, and let's do it. Okay, so I've roughly plotted my data points here, and don't stress about it too much, just get it close enough. And I know it's going to go through 0 because of the structure of how my equation works. I want to do a best fit line. It doesn't have to go through every point, and please don't do a connect the dots zigzag line. This needs to go through the middle, and so I'm going to do something that looks roughly like this. Just quick and dirty. Okay, and now I'm going to try to communicate a little bit to my grader about what am I actually trying to show here. So we've gone through and we've graphed it. Now we want to use the graph to calculate the value for the mass of Saturn. Okay, so I'm going to go ahead and just coach them up a little bit about what I'm doing, and then I'm going to show them on this graph what I'm doing too. So I'll do that real quick. Okay, so I'm just going to take a couple seconds and rewrite my equation that I'm using to like inspire me for how to like find this constant. And I'm just going to go ahead and come on over here, and I'm going to go ahead and draw that too. So I'm going to pick a point on here that looks like it's a nice fitting spot here that I can find the slope for. So I know it's going to go through 0, so I'm just going to go all the way up here, bing. And all the way over here, I'm going to say, hey, this is my rise, and this is my run. And I'm basically going to use this point right here. It's pretty close, and I'm going to use those values to calculate this. So I'll throw those numbers here in just a second. All right, so I wrote this out, and I'm just showing real quick that hey, this equation I came up with, that's the rise and run of this. And so I just made sure I diagrammed that and just showed it so they can see what I was doing. I see that my best fit line neatly crosses exactly this point right here. So I'm going to grab those points from my graph. That's my rise and run. I'm putting in what it goes up 20, e to the, oops, I said 62 there. That is not good. It's 26. Let me fix that. Apologies. E to the 26th is what this graph would give us. 20 e to the 26, okay? And then I come over here and then I plug in my run, which is it goes across at 3 and 3 quarters. So I'm going to put in 3.75 there. No funky units for that as far as like times 10 or whatever. And then I just throw in the units here for the vertical, for the rise, I get meters cubed. For the run, I get all this gobbledygook down here. And I see that right away I'm going to cancel out some meter action. And I want to look a little more carefully what I have left. I see that I have this Newton in here, and Newton is a derived unit. So I can explain that in terms of Newton's a force, so mass times acceleration here, and so meters per second squared, and I flipped it over because it's on the bottom here of this fraction. And I can see from that point that I'm going to have a bunch of stuff cancel now. Boom. Oops. We'll grab my pen here. And so my meters are going to go away. My seconds squared are going to go away. My kilogram here and here, and I'm left with this kilogram. So I get the kilograms for my units for the mass of Saturn, which works out a-okay. And I really like my answer because Saturn is probably very big, and it's a lot of kilograms. Okay, so at this point, man, we are done. So basically, how this will always work, here's how you identify one of these linearization problems. They're going to have a data table, and you're going to need to fill in a couple of spots, okay? You're going to have a giant graph that you need to graph, and you're going to find the slope of that graph after you've linearized the data. And you're going to use that to calculate some constant. In this case, is the mass of a planet. Basically, you take whatever relationship you have for the context they give you. In our case, we had a moon orbiting a planet, so we had centripetal acceleration, and so we plugged in force of gravity and what it meant to have centripetal acceleration and to go to orbit one circumference in a period. Plugged in all that stuff, and we're actually able to come up with a way to isolate for our constant for the mass of Mars, and we basically put everything else besides that constant on top or on bottom, and those are going to define what our vertical and horizontal axes are. And then once we do that, we can go ahead and plot that stuff. It should be in a straight line at that point, and make sure you communicate you're doing rise over run stuff, and plug in those values for in between any 2 points on your graph there, and you can find your slope, your constant. So I hope you can recognize these types of problems. You'll be super confident about how to generally approach them, and I hope this is helpful for you. Thanks a lot.